All right, go ahead and draw this. So in order to answer this question, we're talking about sp2 hybridized. You need to be able to do what first? Draw the Lewis dot structure. You're going to draw the Lewis dot structure first. See if you can do that. Got them all? Okay. We got them? Nh3 is one we've done a lot, right? Okay. What's the hybridization on the nitrogen in this one? sp3. I have 1, 2, 3, 4 equivalent pairs, regions of electron density. This is going to be sp3 hybridized. Okay, let's do the next easy one, N2. What's that going to be? sp hybridized. I have 1, 2 regions here. This is sp hybridized. HCN. Okay. Y'all okay with that? I'm looking at the nitrogen again. What's this hybridization of the nitrogen? That's also sp. All right. Now, our smart brains here, we're all AP chemistry students here. We all understand by elimination, obviously NO3 minus 1 is the answer, right? But let's go ahead and work through the Lewis dot structure and make sure that everybody actually has the right Lewis dot structure. Okay, so we're going to work on that. That's what we're here for. Let's put nitrogen in the middle, yes? And O, and O, and O. Nitrogen has how many valence electrons? 5. Let's write it up here. Let's do N5. Oxygen has 6, 6, 6. And the charge is, so I'm going to have one more here. I add all those together, what do I get?
24.
How many?
24.
Are we sure this time? 24. All right, I got 24 electrons. Let's go ahead and place them. Okay, I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Is that enough?
No.
But everybody's got 8, right? But I still need to put some more electrons, right? Let's do that. Let's add another bond here, because that's how we do these. All right, so I have a 24 minus, I'm going to put in a double bond here. Got 24 minus,
8.
everybody good with that? That we're minus an 8? Yeah, all right, minus 8. Minus 8 gives me how many? 16. I got to place 16. Now, this nitrogen's happy, right? Nitrogen's already happy. So nitrogen can't take any more electrons. Can nitrogen have an expanded octet? Nope. So nitrogen's done. We're done with nitrogen. Let's go ahead and place these 16 just for fun. 1, 2, 3, 4. That's 4 of them. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And of course, we've got to do our fun little bracket. -1. And you would, to draw it completely, you would have to draw all the 3 possible resonance structures. We don't need to do that because the question doesn't ask us for that. It just asks us for which one is sp2 hybridized. Looking at this, I can see I have how many? 1, 2, 3. This is sp2 hybridized. Okay. The p orbitals, one of the p orbitals of nitrogen remains unhybridized to form a double bond space, right? But all you got to do is count these. 1, 2, 3. It's sp2 hybridized. That's what the question asks. Everybody okay with that? All right, cool. Let's try the next one before I fall down. Maybe. There we go. What's the hybridization of the Cl in this molecule? That is ClF3. So in order to answer this question, the first thing you need to do is do what? Remember, you're going to always make sure electrons are found in pairs, right? When we get done, electrons have to be in pairs. So let's see what you did. Interesting. Remember, I'm going to try the other method. So we did the counting method a minute ago, which works all the time. It's just not as fast as it could be. Let's go ahead and place our electrons. 1, 2, 3, 4, 5, 6, 7. Okay. What do we know about chlorine? Chlorine can have an expanded octet. I need to place 3 fluorines. So the first one is very obvious. Okay, obviously. But I need to place how many?
3.
I need to place 3. So I'm going to grab this. And this one. Okay. So do all my electrons have buddies? Everybody's got a pair. Every electron has a buddy. Remember, that's one of your jobs, is to matchmaker all the electrons so they're all happy together. Now, I'm going to look at this, and I'm going to say, well, how many regions of electron density around the chlorine? 5. I have 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And if it's going to be 5, it's going to be what? DSP3. What's that? Yeah. So that's when you know you're in the chemistry groove, is when drawn Lewis dot structures are just relaxing. So it's okay. Just takes practice and thinking. But really, if you'll, again, make sure all the electrons have a buddy, and you don't use extra electrons or end up with extra electrons. Okay. All right. Let's see what else we got.
That seal looks pretty.
Atoms that obey the octet rule and that are sp3 hybridized form how many pi bonds?
I still don't understand that. 2?
So it has to obey the octet rule, and it has to be sp3 hybridized. And if that's the case, how many pi bonds do we get?
Wait, 4. Yeah, it could be up to 4, right? Yeah, because it's like single bonds. Yeah, like the one in the middle. Wait, single bonds don't have pi bonds. I thought. Yeah, single. No, the double bonds have.
Yeah, double bond and triple bond.
Wait, double bonds. But single bonds are sigma.
Yeah.
Yeah.
Sigma.
So 0. But if it's sp3, you could also have a double bond.
Well, let's talk about this. So
Oh yeah, because like the
let's think of sp3 hybridized means I have how many regions of electron density?
4.
4. I got 4 regions of electron density, right? So I'm going to put some random atom. Okay? Or maybe put those, right? Any of those are equivalent, right? All right. So if I've got 4 regions of electron density and I obey the octet rule, strictly obey the octet rule, right? That means I can only have how many electrons? 8. So I can have this. This is an option. I can have this. I can have this. Okay? How many pi bonds do you see there? How many pi bonds are here? None. How many are here? How many are here? None. All of these are sp3 hybridized. And sometimes it helps to see real molecules, right? So CH4, our methane, that is sp3 hybridized. I can only have pi bonds if I have a double or a triple bond. So if I can only have single bonds or lone pairs, those aren't going to be pi bonds. So this is our good friend H2O. It's that one. And this one we just drew. What's an example of that? Nh3 ammonia. Y'all okay with that?
Yes.
All right. It's all about getting those Lewis dot structures down. Follow the octet rule first. See if it can be an expanded octet. Make sure all the electrons are paired. For the purposes of this test, that's your job. Make sure all the electrons have a buddy. Okay? Sometimes I've been doing electron or Lewis dot structures, and I find these electrons and they're away from each other. I rearrange them to make them a buddy. Put them next to each other, because it can be hard if you start counting and you're checking your structures. And I got one electron over here and one over here. As far as the structure is concerned, I mean, as far as the molecule is concerned, you don't care because they'll pair up. But go ahead and erase it and redraw them. All right, let's take a next question here. Where did I put my clicker? There it is. What is the hybridization of the central atom in ICl4? -1. I guess you guys showed up. All right, so let's go ahead and take a look at this. Everybody has something written down. You good? You got something written down? All right, well, let's check this and see if we know what we're doing. So I've got iodine, which has 7, and chlorine. Everybody okay with that? So how many is that?
36.
Does everybody agree with that? All right, 36. All right, I got 36 electrons. I'm going to put this over the side. We're going to check it out. But first of all, who's likely going to be my central atom? Iodine. I think it's a reasonable assumption. Iodine is going to be my central atom. I'm going to go ahead and do this. Okay, and I've got 4 of these guys to get placed. Cl. Actually, I'm going to move this over because I don't like writing right here. All right, so I'm going to I. Cl. You okay with that? Good with that? That's the first one. How many more do we need to place?
3.
What's that?
3 more.
Oh. 3 more. 3 more, right? So I'm going to put Cl. Okay. And I need to put another one out there, right? So I'm just going to throw another one here. And that I just brought, that's my little extra electron that I brought in there, right? And what's the charge on that? -1. Okay. It's very pretty there. All right. So I look at this. All right, it's kind of like life. All right. So we got this here. How many regions of electron density around the I? 6. That means it is D2 sp3 hybridized. By the way, what kind of shape is this? That's going to be square planar again. You like that one. That's just one of these days. I'll put one on the test just for you. So once again, that's this one here. It's going to end up being square planar here. I've got the chlorines and then the iodine in the middle and the 2 lone pairs up and down. That's your square planar. We use that a lot, right? We okay back there? Okay. Good? All right. If you can draw Lewis dot structures, this is pretty straightforward. All right. Draw these wonderful, fun structures and tell me which of the following has 2 pi bonds. Got some Dr. Pepper in me, and I got some coffee in me, so we're in good shape.
I finished mine.
Yeah.
Sad. See, these are too intricate for me. Like,
Nice little sippy cup.
yeah.
I find these kind of
It's my method. Pretty sure she got it from Target. Oh wait, actually.
We should get a class set and put some decals on it.
I agree. Oh my god.
Do some cricket. We got a cricket at the house, so
Wait, why do you need a cricket?
to cut the vinyl decals.
Oh, I thought you meant like an actual cricket, like as a bug. Oh. Like, I was like, Dr. Cloud. It's a cup. No. Nope. There's a Butter's cricket story. Yeah. That's scary. Can't stand her. Is that actually? Did I do that right?
But the first one? Yeah, first one's right. And actually, they're in great order to do this, so it's really helpful to move. Of course, y'all can do the bottom one too. Yeah, you should be able to draw E.
yeah.
Oh. Wrong.
That's methane.
It is methane. CH4 is methane, yes. How many pi bonds are in that? How many pi bonds are in methane?
No pi bonds.
No pi bonds, yeah.
Big ring.
You got it? Very good, very good. Good? You got it? I don't even know what that is. Oh, yeah, you ask a question. Nope. Seems a little complicated.
Then you always pick one person to like ostracize from the group.
I know which one it is.
Nice. All right, let's try this. Let's go ahead and do this. I'm going to do E first because it's easy, and that way I can do it and, you know, look like I know what I'm doing.
But you know it doesn't happen.
All right, how many pi bonds? So pi bond has to be either a double or triple, right? So how many pi bonds are there? Zero, so we'll get rid of that one. All right, let's come back and we'll do A. I have C2H6. One of the things I know when I'm drawing Lewis dot structures, little things you put in the back of your mind, is hydrogens are always going to be on the outside. Because they can only have what? They can only have one bond. And that's also true for fluorine. So fluorine is going to only have one bond, so when you're dealing with fluorine, it's going to go on the outside as well. Chlorine, bromine, those guys can have expanded octets. They can often be in the middle. Yeah, they make life fun. All right, so that takes care of that one. But let's take care of carbon. So if I've got two carbons, I'm going to put them in the middle. Carbon. And I've got 6 hydrogens. So I'm going to put 3 on each side. Very good. And is everybody happy? Yeah. That's my structure. How many pi bonds we got?
Nope.
No pi bonds. Get rid of that one. What's that?
We're going to start doing like the really stupidly complex Electron structures. Like caffeine.
Let's
Yeah.
not bring it up.
So organic. So you'll be doing this in organic chemistry.
This?
No, you'll be drawing that.
No.
You'll be drawing those structures.
No.
Okay.
That's like.
But it'll tell you. So we commonly call that caffeine. There's actually a word for it that tells you how to start, how to go around the ring, and where the double bonds are going to be. Yeah.
If you say that we will start drawing these in organic chemistry, we are not in organic chemistry. If there's a question on one of the texts, we'll have that.
So I don't. If I show you the structure, like this one here, can you guys see this well enough?
Yeah.
How many sigma bonds are there?
Wait, okay. Is sigma bonds? Is that just a
Uh-huh. But remember, double bonds and triple bonds also count because one of those are sigmas.
all of them?
All of them.
Oh, I'm not counting that.
All right. So there's
What?
4,
Right.
Oh.
4,
Wow.
8, 12. Good. All right. I'm going to start here. 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24.
I thought where they overlapped was a double bond.
That is.
There's only one.
So it's 24 sigmas. Let's how many pies? 1, 2, 3, 4. 4 pies.
Oh, I get it.
Wait, isn't there? I think didn't last time, like we learned about sigma and pi, wasn't there? Or no?
No. That's all. So we just kind of threw that out at you. All right, let's take a look at this. C2H4, right? Let's take a look at this one. I'm going to get rid of these H's. Put a double bond here, and that's C2H4. So how many pi bonds are here? There's 1 pi. How many sigma bonds are here?
5.
1, 2, 3, 4, 5. 5 sigma, 1 pi. Again, not our answer. Let's go ahead and take care of this. Let's get rid of these 2 hydrogens. Okay. That is C2H2. All right. How many sigma bonds?
2.
There's 3 sigma bonds. 1, 2, 3 sigmas. Every bond's a sigma bond,
Right.
right? And then the pies are whether or not I have double, triple. How many pies are here?
2.
There's 2 pies. Or C. Let's go ahead and just for fun do the next one.
It looks funny.
C3H8.
What's the name of that?
C. So let's do.
Probably a much more organic name.
Yeah, octahydride.
Did we get it right?
Is that right?
Yes. Your C's are getting
Sure.
How many sigma bonds do we have?
1, 2, 3, 4, 5, 6, 7,
Quite a
8,
lot.
9, 10.
8 plus 3 is 11. 8? Girl, where'd you get?
I don't want to count.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
Oh, so close.
Just subtract one.
Yeah.
Yet so far
Wait, what
away.
is that one called?
I don't know.
Tricarbon.
Now when you see these things, you start using the organic names.
Yeah.
So which
Like
is
methane.
tricarbon.
No.
No, like what's that? Like maybe it's like
Because C6H6 is
Try.
benzene.
ibuprofen. I don't know.
No.
Hank Hill. Hank Hill.
Painkiller?
What's the
It's a
name?
Hank Hill.
Oh,
Painkiller?
that's
The name is Painkiller.
Hank Hill.
painkiller.
Who's that?
Painkiller?
Have you heard of King of the Hill?
Yeah.
Yeah, the guy with the glasses.
That show me good.
What does he do?
He sits on a hill.
What does he do for a living?
He drinks beer.
That's not what he does for a living.
He has a
Seems
little
like
chubby
it.
son.
He sells what?
Drugs?
No.
Painkiller.
Oh my god.
Let's give him a
Do you know what he does?
No, I actually don't. I've never watched that show before.
He sells propane and propane accessories.
So that's propane?
That's propane.
Why did you say that?
Because I thought y'all would get that. I thought we'd do something that was culturally relevant, but I realized y'all are much too young for cartoons.
I know the show, except I didn't like watching it. It was boring. I didn't think it was. I like Family Guy.
All right. Good. Let's do the next one. All right. Which of the following statements is true?
Okay, that was already wrong.
Wrong.
I don't know what that means.
Oh, what? Skip.
Okay. So I want y'all to read these. Make your guess. Make your guess,
Okay.
and then we'll have one of y'all come up and explain it
Oh, you.
I sacrificed Justin.
in public.
That's good.
Yeah, let's sacrifice the senior.
I can explain why the first one's wrong.
Hi, man.
Good. I'll let you do that.
You have less of a life to live.
Zach, it's you.
It's not A.
You have to go.
It's just not you.
B is
No,
just
you
worded
lost
and
this
they'll make
year,
it play a
so that's
boss.
how it works.
Why tell me? Do you want iced coffee?
That's not gonna work.
You want the melted ice left over from the iced coffee?
Is that like the cool ice that you usually do in the video?
All right. Let's see. Is A true?
No.
No. It should have. How do I make it? How do I fix it?
It should have
Two pi bonds and
Switch it.
one.
2 pi bonds and 1 sigma bond.
You know what? I'm gonna change the words.
Yeah.
That way I don't have to draw Greek letters. All right. What about B?
Good question.
Just a weird.
I think that one's true.
I'd assume kinda.
What does that
It would
even
make
mean? It's
sense.
true?
Okay. So let's put a little dash here because we're not sure it's not true, right? We're gonna keep going. We're gonna practice our test taking strategies.
You're a more right one.
So, does free rotation occur around a double bond?
What do you mean by free rotation?
Free rotation. So on these no, not resonance. These guys can actually spin.
I mean, no, you probably couldn't pull it off. The double
So
bond.
if I've got a double bond, they're locked.
Yeah, because then they can't.
They can't move. So free rotation is not going to occur. Okay? I'll just put a knot there. It may like me life, right? It can occur around a single bond, but not around a double bond or a triple bond. There it is. Pi bonds have electron density on the internuclear axis.
Oh, true.
I don't think so.
No, I don't.
All right, let's go back again. Remember those pictures, those really pretty pictures we had? Those nice three-dimensional pictures? So I've got my atom here, my nucleus of this one and of this one, right? Okay, that's my central overlap. That's my sigma bond. The sigma bond creates this bond here, right? Remember, your pi bonds are here. Remember, this is my pi bond here. Okay? Is that overlapping on the central plane? No, it's above or, above and below or left and right, however you want to think about it. It depends on which one you're talking about. So this is not true, which brings us back to this, which is what I just drew here. This is my sigma bond. This isn't a head-to-head overlap of the atomic orbitals. It's in a straight line between the two nuclei. Yeah. Yeah. Zach. Do that for me. Hey, that way I don't have to stop and ask a question. I can just, yeah. Okay. Y'all good? This is the answer. Cool. All right. Which of the following has the shortest NO bond? Remember, bond length, bond strength?
Oh yeah.
There's a question
Triple
on
bonds shorter.
On one of the problems.
Internuclear distance.
That's okay. Don't put it like that.
Didn't we just draw that one?
Yeah. Draw the Lewis dot structures. Good? You got the structures drawn though? Okay. Let's take a look here. So I've got NO3 minus 1. Right? We just did this, right? And I know that needs to be resonance, but that's okay. Y'all okay with that? All right. Let's do NO. What do we notice about that? One less electron, so this would be 5, and this would be 6, and then I have minus 1, so I should have a total of 10. N. Is that what you got? And again, let's go through that real slowly just for a moment. I'm going to have N and O. That's my 10. This is why we did this over here. Minus 2. That leaves me to place 8. So 1, 2, 3, 4, 5, 6, 7, 8. Nitrogen's happy, but oxygen's not. So we'll go through this process again. Okay, and I'm going to put another one there. And so this is 10 minus 4 is 6. 1, 2, 3, 4, 5, 6. Again, nitrogen's happy, oxygen's still not happy. Let's get rid of that. Put a triple bond in here. This is 10 minus 6. That leaves me with 4. 1, 2, 3, 4. Okay. This is a triple bond. Let's do NO2 minus 1. NO2. So this case, I've got nitrogen. Okay, and I've got, this is a minus 1, right? Okay, what can we do now? Double bond what? Okay, so let's double bond this. Is everybody okay now? Is that what it's supposed to look like?
Wait, no.
Wait, what? Huh? 2, 4, 6, 8.
No, we gotta take one away.
So, NO2, N has how many? 5, oxygen, oxygen, and we got an electric, we got an extra one, right? So this is
18.
You sure?
Yeah.
18. All right. So 2, 4, 6, 8, 10, 12, 14, 16, 17.
15, 16, 17, 18.
What?
So what should we put?
Nothing. A double
Where?
on the other one.
If I put a double, let's do this. Let's do this. Hey, no, let's talk about this. If I put a double bond here, what's happened to nitrogen? Has too many. Okay.
Put another electron.
Oh, put another electron pair. I had it right.
Wait, I thought you already had a pair there.
No, it was like.
I just had one. Yeah.
You just have one electron.
What's that?
Why was it too many for the bond?
Let's do that. Let's look at it. So if I do that, now I have 2, 4, 6, 8, 10. And nitrogen cannot have an expanded octet.
I said it was too much for oxygen.
No, it's fine. It was fine for oxygen. Okay. And again, we'd have to have a resonant structure. All right. Shortest bond is going to be what? NO plus, right? Because it's what kind of bond? It's a triple bond. And we know that the triple bonds are stronger and closer together.
The more kind of bonds you have, the more.
Right, it's being pulled together. So you can imagine this overlap. The sigmas are being pulled together, but then the pi's are pulling together up here, and then the pi's are pulling together on the sides as well. So they're really pulling that. This is the shortest and strongest bond here.
There was a question like that.
Yeah,
It's harder to put
But it was like greater.
exactly. Good. So drawing the Lewis dot structures, being able to do that fairly quickly is going to be very beneficial to you. All right, another thinking question here. Which of the following statements about the carbonate ion is false? So first thing I would do is draw the Lewis dot structure. Draw that Lewis dot structure for carbonate. That's going to help you out. Good? No? We got the structure drawn?
Kind of. I kind of forgot.
Yeah, I got it. Wait. Is it like this? Yeah.
All right, let's look at carbonate. Did y'all get that? Have y'all drawn carbonate before?
Yeah.
No.
No, let's back it up then. Well, that's what you should look like. That's what we're going to end up with. Let's take a look, though, and see what's going on. Blank. Carbonate. Let's write our formula up here so we can keep that in mind. Okay? Carbon's going to go in the middle. Makes sense. I'm going to have an oxygen and an oxygen and an oxygen. Let's go ahead and add up our electrons. Carbon has oxygen and
24.
you sure? Are we okay? All right, I got 24 electrons. Good? So let's go ahead and take care of that. I'm going to take care of this. If I have 24, I have 2, 4, 6. That's 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 14, 15, 16, 17, 18. Okay. Everybody happy?
No, carbon's not.
Carbon's not happy. Carbon's not happy. But we're only off by 2. But 2 is 2 too many. Let's make this a double bond here and minus 8. That leaves 16. All right. I need 1, 2, 3, 4. Oxygen's now happy. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. This is my structure. It has a -2 charge. Yes?
So I forgot what you said last time, but correct me if I'm wrong. You never put extra electrons on the central atom, right?
No, you stick them on the central atom. Be okay. It's okay.
But if,
This carbon can't have an expanded octet anyway. It's all filled, right?
then where do they go?
There's no extra electrons.
What about the 2?
It goes on the oxygen.
They had to go on the. I had to have 2 extra electrons to take care of this oxygen, right? One of them here. Remember when I build oxygen originally, all the oxygens want 2 bonds. If I throw it an extra electron, though, it doesn't need that. This extra electron satisfies that bond. So these 2 electrons, this one's happy because it has a double bond. This is what oxygens like to have. They like to have 2 bonds. You know, 2 single bonds with hydrogens, double bond with carbon. They want 2 things to bond to because they need 2 more electrons. All right. So there's my 2 extra electrons. Now, if I was drawing this, if I told you to draw the structure of carbonate, would I be finished? No, I'd have to do what? We got to do resonance structure. Okay. That's carbonate. That's carbonate. Not just that, all of it together. It's impressive. What's that?
When do we know how to draw all of the resonance? Like if you ask us like an FRQ, like draw this.
If I ask you specifically, draw the Lewis dot structure of carbonate, or sulfate, or anything that needs a Lewis dot structure, resonance structure, you need to draw the whole thing. But if I ask you, like, with just one of these, you could tell me what's a hybridization of this carbon is. What is a hybridization of this carbon? sp2. I have 1, 2, 3 regions.
Oh wait, I'm done.
So this is sp what? 2 hybridized. But I can look over here. This is also sp2. This is also sp2, right? Okay. What's the angles here? What's going to be the angles here? What is this angle?
120.
120. Good job. How'd you know that? Okay.
No shame about it, Jessica.
Yeah, they're going to be equal distance. All right. You good with that? Yeah. So the questions, I think one of them was, it had 24 electrons. Is that true?
Yes.
Okay. Yeah, so the ion has a total of 24 valence electrons. It does, in fact. The orbitals on the carbon are sp2 hybridized. Do you all agree with that? That's true. All right. Do you believe that one CO bond is shorter than the other?
Wait.
Yes, they're double bond.
Yeah.
Yes,
They're
because
double
of
bond.
Well, yeah, because but the resonance structure.
But it's only talking about
Oh,
the
yeah, the
single one as
resonance.
well. There's a single
What?
bond.
Because the resonance is like,
Huh?
they're basically all this, right? They're all the same length.
Imagine the real structure are these 3 things laid on top of each other. Each of these has an equivalent bond of 4/3, right? So it's shorter and stronger than a single bond, but not as short and not as strong as a double bond. This isn't the actual thing that's going on with carbonate is overlaid. Imagine all 3 of these structures overlaid each other.
Like, then why don't we just draw them with like a shorter line?
Well, because it's tough to see. Is that a third? Is that a quarter? And it's not really exactly that. We just know it's more than one less than the other. Okay? All right, so let's take a look here. So the point here is these bonds, and this is why I draw a resonance of a Lewis dot structure. In the real structure, these are all equivalent. It's not like I can go in here and break this bond. It takes the same amount of energy to break this bond, and this bond. They're equivalent bonds. That's why we have to draw all 3 of them to get the actual structure going on. Okay? And that leads us into our actual new lesson for the day. We're going to be using the localized electron model. There are some significant limitations. This is the big one. Right? So it assumes incorrectly, and I think I've told you all this, but it assumes incorrectly that electrons are localized. We know once a molecule forms, though, the electrons are sort of part of the molecule structure, not as much part of being around an individual atom. And that's what we had before. We talked about the electrons being around this atom or that atom. Once it forms a molecule, the electrons create a new space. Anyway, the localized model has some issues, all right? It doesn't deal effectively with molecules containing unpaired electrons. Thankfully, you're not going to have to worry about that. And it doesn't really provide us direct information about bond energies. We kind of infer that. We talk about things being relatively speaking, a double bond, triple bond, single bond, right? It doesn't really help us out with that. So there is another model. I'm going to blaze through it pretty quickly. Hopefully we'll finish this. Okay. Molecular orbitals. They're going to have the same characteristics as atomic orbitals in that they can hold 2 electrons with opposite spins, and the square of the molecular orbital wave function indicates electron probability. Also, we're going to have 1 up, 1 down per orbital. So those rules sort of still apply. It's going to look a little different. We're going to move pretty quickly, though. I'm not sure.
This is weird anti-bonding thing.
Right. So we have a probability of bonding and antibonding. Page 6, y'all said?
6.
All right, page 6 and 7. That's what she said. All right, here we go. 1sa and 1sb. We have an antibonding and a bonding. The likelihood that the electron orbitals are going to overlap each other and create a bond, or they're going to be against each other. All right. Yeah.
Antibonding also being called repulsion.
Called what?
Repulsion.
Don't. Just because. I don't want you thinking about this too hard. I just need to expose it to you so that I taught you chemistry. We use a localized electron model exclusively in the AP test. So just this is for your personal.
So you're just doing that thing that science teachers do, where you tell us about something, but you're not going to explain what it is. You're just going to leave it to like the higher.
It's probably better if you don't explain.
Well, you're going to learn this in general chem next year. Well, not next year for y'all, but 2 years from now. But you need to know it. You need to understand. Because it's like, why do you use a localized model if there's all these issues? Well, because when you move up to the next higher model, it gets a little more complex. Okay? So we'll talk about that. All right. So the properties of electron models, molecular orbitals of hydrogen, is a probability that both the molecular orbitals is centered around the line passing through the two nuclei. All right? That's that sigma molecular orbital we just got finished talking about. In the molecule, only the molecular orbitals are available for occupation by the electrons. All right. I have a total of 2 electrons available. If I take H2, put the 2 hydrogens together, I only have 2 available. And they're going to occupy this space here. That is my MO1 space. That's going to be the one that is a bonding. That means we're going to have a bond. What's neat here is when you can use this either for homodimer or heterodimers, I can actually use this model, draw the electrons, and tell you if this bond is going to happen or not. Like, I can actually describe to you whether these things are going to get together or they're not. All right, bonding. Bonding molecular orbital are lower in energy. And remember, chemistry, atoms, just like the rest of us, just like humans, we want to attain the lowest energy state possible. The antibonding, they're higher in energy than the atomic orbitals. The electrons in this orbital favor the separated atoms. If the electrons are if you have electrons down up there, they would rather stay apart. Electrons down here would rather stay together. The lower energy would prefer the bond to happen. All right. Bonding and antibonding molecular orbitals. This is my energy. All right, I've got my bonding down here, my antibonding here. The energy, this is for a homodimer. We start out with 2 equivalent energies. Homo means what? Same, good. Yes. Homo. So there's a homodimer. So homo is 2 things that are the same coming together to form a bond. And heterodimer is 2 things that are different. So we're talking about different atoms. All right. There's a high probability of finding electrons between the nuclei in the bonding. Electrons outside the space between the nuclei. So I've got this space. Well, right. Okay. These electrons are going to be bonding. If the electrons are found here, we're going to call these bonding electrons because they're holding the nuclei. Remember, the nuclei is going to be positively charged. It's going to be negatively charged. It's going to be holding this thing together. Okay? Good.
So bonding electrons would be found in the
Yeah. All right. So labels on molecular orbitals can talk about their shape, the parents, and whether they're bonding or antibonding. And we talk about antibonding. It's the same thing. We just put an asterisk when we talk about antibonding. All right. We can write molecular electronic configurations the same way we do atomic configurations with the S's and the P's and those kind of things. They can hold 2 electrons and the spins have to be opposite, just like we've done with atomic ones. Molecular orbitals are conserved. We're going to have the same number of atomic orbitals. So if I have this over here, which has a 1s, and this over here, which has a 1s, I'm going to have 2 orbitals because I had one from this one and one from this one. Y'all follow me? However many orbitals this guy started with and this, we put them together, and that's how many we're going to have in total. We'll start seeing it when we see some charts. All right, so I've got hydrogen. I started hydrogen with its 1s and another hydrogen with its 1s. They each had an up. They come together. This is our bonding. I now have 2 electrons in the bonding orbital in the sigma 1s bonding orbital. I have no electrons in the anti-bonding orbital. All right? We'll sketch a couple of these and then we'll kind of be done with it. All right. Bond order tells me how many bonds I'm going to end up with. So I have the number of bonding electrons. I subtract the number of anti-bonding electrons. I divide by 2. So in the case of hydrogen, I had how many? How many bonding? 2. How many anti-bonding? 0. 2 minus 0 is?
2.
And 2 divided by 2 is?
1.
Hydrogen H2 has a single bond.
Is it possible for bond order to become negative?
No.
Okay, so
Y'all okay with that? Because you're always filling from the bottom first and your bottom's your bonding. You can have it as 0, which tells you the bond doesn't happen. Yeah.
Can we do another one like that for you?
Oh yeah, we're going to do a lot.
Wait, is this gonna be on article?
Might as well.
No.
Is it on the equation sheet?
Yeah. Wait, have you decided what our test is gonna be?
is it this thing? Oh,
Oh. What's that?
in order that this is like the order that we filled them in?
Yeah. Yeah.
When's our test? I have to mentally prepare.
You have what?
When's our
But
test?
it's like
I have to
over
mentally
what we're
prepare.
doing.
I don't know, Wednesday of next week maybe. What's today? Thursday? So we have Monday. Yeah, we could probably do Wednesday next week.
So is Monday gonna be a review day?
It'll be a something day.
Next week?
All right.
Wednesday. Friday.
Let's take this. Let's now look at the H2 minus 1. That's what this is. So H2 minus 1. So H2 minus 1 means what?
One more electron.
I've got an extra electron. Let's see what happens here. If I have an extra electron, I've got 2 electrons from this one for some reason. I stick them together. I have the 2 bonding electrons. I have 1 anti-bonding electron. So 2 minus 1 divided by 2 is 1 over 2. How many bonds is that?
0.5.
Yep. So homonuclear diatomic molecules, 2 identical atoms. It's called homodimers. Only the valence orbitals of the atoms contribute significantly to the molecular orbitals. This is what we've taught you since you were in 8th grade, right? Valence electrons determine bonding and reactivity. Make sense? All right. Here's our boron. Boron is described with some p orbitals. They occur in these sets. 3 mutually perpendicular orbitals. 2 pairs of p orbitals can overlap. Yes, boron is weird. Notice what is it missing? What does boron not have? Okay. Consider these molecular orbitals from a head-on overlap. Anyway, I'm gonna flip through this a little bit. I just want to show you how to do it. Pi molecular orbitals are your P's. Molecular probability lies above and below the nuclei. This is where I'm like, remember this is what we did. Talked about being here and being here. And that's your center line, right? Okay. So I would draw that. So here's our boron. Each boron has the 3 P's. So I've got one of the two P's, the sigma, right? I've got the P that's there. Okay. This one up, one down. This space, one up, down. That's the same space as that. And then imagine there's a space here. Let's see, like that. And then that's an up and a down. Okay? That's all the pieces come together. So one of the P's are overlapping this way directly. The other ones are up, and the other ones are across the side. All right. So how many electrons does boron, how many valence electrons does boron have? 3. 1, 2, 3. And this one also has 1, 2, 3. How many total do I have now? 6. Let's fill from the bottom. 1, 2, 3, 4, 5, 6. Is this bond going to happen? Let's see. Actually, I forgot I needed to fill the other two first. Yep. Top and bottom first. All right, so here's our sigma. Let's do our sigma first. 1, 2, 3, 4, 5, 6. There we go. So how many bonding do I have? I have 4 bonding, right? 1, 2, 3, 4. I have 4. And how many antibonding? 2. Divide by 2, that is 1. So B2 has how many bond? A single bond. Cool.
Are we gonna have to like draw the shape?
Yeah, you'll sketch it out. It's real, I think it's in your homework. It's good stuff. When's that due? Last night?
Yeah. There was not one of those.
Oh. Oh, that's right, that's right. This is next one, yeah. That's this unit. All right. This should be a stable molecule with a single bond. This is a stable molecule with a single bond, and in fact, that's what happens in real life. It can be. It doesn't have to be, though. The Brinkelhoff guys, those, when I say hydrogen, H by itself doesn't exist or doesn't exist for very long and free in the free world, right? And in its free state, hydrogen is going to be H2. Okay? Boron can be by itself, or it can be a homodimer, or it can be bonded to something else. All right. Types of magnetism. So we did that like really quickly. Types of magnetism in the presence of a magnetic field. Paramagnetic and diamagnetic. All right. Paramagnetism. Substance is attracted into an inducing magnetic field. Almost everything is magnetic. See, we talked about ferromagnetic. Now, ferromagnetic is the typical magnets we're thinking about. That's this guy, right? Okay? As opposed to, but actually, lots of things have magnetic properties. So they can be paramagnetic or diamagnetic.
I remember seeing an experiment on this where they figured out if water was paramagnetic.
Yeah. So you can actually test that by looking for unpaired electrons. If when you draw your orbital diagram, orbital notation, you see unpaired electrons, you know it's going to be paramagnetic. It's going to be attracted to the magnetic field. If all of the electrons have a buddy, if they're all paired, it's going to be diamagnetic. The substance that has both paired and unpaired electrons has a net paramagnetic property. So just like we did with individual atoms or individual elements, we also can do with molecules and figure out who's paramagnetic and diamagnetic. So it's going to appear heavier because we're going to turn the electromagnetic sample on. I don't care. I'm going to show you a nice, pretty picture. I'm going to show you a little video because I think it's fun. Diagram explains the observed paramagnetism of B2, right? So paramagnetic means we have unpaired electrons, all right? So I've got these situations here. When BS mixing is allowed, these energies of these orbitals are reversed, and 2 electrons now occupy a separate space and still have parallel spins. All right, we're not doing that, and I really don't want to dig into this. We're not going to dig into this a whole lot. I just want to talk about, I just want you to see this, read that chapter, okay? This is important. Just because I have a bond order, I can't talk about specific bond energies. This is a triple bond. Oxygen's paramagnetic. About that, click through that, the orbital diagram model. I've got neon. Yes?
Can you go back to the slide that you said is very important?
Which one?
Bond order. No. I want to know about bond order.
Oh, just keep in mind that bond order, when you do this, bond order is not going to be giving you a particular energy. All right. N2, right, has a triple bond. If you build N2 with a molecular theory, you're going to see its bond order is 3. And we can all do that with Lewis dot structures too, right, if we keep that in mind. And we notice that oxygen is going to be paramagnetic. Let's see. I'm going to use the molecular orbital model. So predict the bond order and magnetism of each of the following molecules. So Ne2. So Ne has 8. Now, our brains tell us, what do we know about neon? Noble gas. And what do we know? What do we talk to? What do we tell the little 8th graders about noble gases?
They're antisocial.
They're antisocial. They don't react.
They think they're above everyone else.
They think they're above everyone else. And of course, us big kids, we know that's only true for, well, that's only true for 8th grade. But helium and our good buddy we're going to talk about right here, neon, right? But let's talk about what we have to do here, neon. So if I wanted to draw a neon, let's see if the pictures show up. 2s, we got 16 valence electrons. Okay. Okay, let's put them in the following. There's our diagram.
I mean, that makes sense, but you said yeah.
So I could actually, we could draw this. I could have the Ne, the S, P. Okay. So this is my S. This is P, P, and P, P, and P, and P, and S, right? So I have 16. So 1, 2, 3, 4, 5, 6. No, that's not the way this works. 5, 6, 7. I think it's 8, 9, 10, 11, 12, 13, 14, 15, 16. This is our, that's what we just did. That was that picture just a minute ago.
Am I supposed to know how to, like...
No, you're just going to know that each of the neons has an S and 3 p orbitals. Yeah. And that's what this ends up being there.
Whatever it's hybridization.
So this is 8 minus 8 divided by 2 is 0. Neon does not hybridize, does not bond. It was not expected to bond, which makes perfect sense, right? So we could do the same thing if we wanted to with chlorine. I'm going to do chlorine just for fun. I've got Cl2, what the heck that is. All right, so I've got Cl, okay, and Cl. And each Cl has an S and 3p orbitals, right? So I'm going to have an S and a P, P and a P, and a P and a P, and a P and an S.
So they don't reflect each other?
So this is S, P, P, P. It's this atom has how many valence electrons? Has 7 valence electrons. If I were to draw the structure, right, I would have 3s, 1, 2, 3p, 1, 2, 3, up, 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 down, down, right? That's chlorine. How many, between these two, how many total do I have? 14. All right, let's start placing them. I'm going to go 1, 2, the S's, we've got to fill the S's first. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, that's not, yeah, 11, 12, 13, how many? 14. All right, how many do I have down here? How many? 8. How many do I have here? 6. 1. Cl.
Okay, the way they do it.
Okay. Draw a Lewis dot structure, and this is one of the reasons that we think this can wait.
They can't wait.
The molecular orbital theory can wait. The problem is, once you get beyond, right, kind of like right where we're right at the cusp of localized electron theory, not being able to answer some of our chemistry questions, what's really going on. So we've got to move on to this new model. Y'all remember that we did the Bohr model, we had the little circles? We drew little circles, we did that in 8th grade. And even when you started with me last year, we still started with circles? Okay. So, and then we told you, hey, this is neat, this is not what the electrons really look like. We have the quantum molecular, the quantum model, right? And so we said, well, electrons don't move around in orbits. They're kind of in these regions, these orbits, these orbitals, right, that are 95% probability or 90% probability, okay? And they're just kind of found there. We don't really know what they're moving because we've got Heisenberg, right? And then we said, think about them hanging around atoms in these particular spaces. Well, now what we're saying is now if I take 2 atoms and stick them together, you can kind of think of them, one way to think about them is hanging around their atoms, and they're just kind of mildly interacting. Or you can understand that when they get together, these electrons become a whole different structure. I mean, related to their initial structure, but a different structure that has a molecular orbital type of structure. So it's a different way to think about this, and it helps overcome some of the limitations of the localized model. That's why we're heading down this road. Yes?
What is this called again? The what molecular?
This is the molecular orbital model. So,
I thought you
as opposed to localized model. So the localized model basically treats electrons as if they're all associated with individual atoms. Somehow, you know, when we draw that, we talked about, where to put the extra electrons on certain structures. The reality is they just kind of go in there and they hang out. But we got to put them somewhere when we're drawing our Lewis dot structures. So we do that. All right, here we go. So y'all do phosphorus. P2.
Wait, on the other one, why did like
Those are anti-bonding. It's in the 3rd row, right? Does it have any D's? No. Let's not worry about D's. It has an S. So P has, I don't know what I'm drawing that for. P is 3S, 3P. that's right. Is that phosphorus? Okay, cool. That's S. This is S. This is P. Do y'all see that? Sigma S, sigma P, pi pi.
Is that like, that's loose order?
Yep.
Oh, it is.
All right, so here we go. How many total electrons do I have between them? I got 10. Let's go ahead and do it. I got up, down, up, down. That's 4. 1, 2, 3, 4, 5, 6. Is that right? All right, cool. How many bonding do I have? How many? I have 8. How many antibonding? 2 divided by 2 is 3. Let's draw our Lewis dot structure just for fun. And then what we do now? It's going to be a triple bond, right? Just like somebody else in the same group, nitrogen. Yes?
If it does have a D, like, would you draw 4 on?
Yeah, this actually opens up even bigger, and they go here. Okay, but I don't think anyone, even next year, even in college, are going to ask you to do that. They really just want you to get the idea that the localized model is still not really what's happening. This is why I teach this, because I really want to emphasize. I'm just a big person on the science. I need you to understand the models are just models. They're just ways for us to think about and process what's going on. It's not that I need you to dig in and know how to use this so much. I just want you to get that the localized model has issues. And that's why we have to do things like the resonance structure. It's to communicate, you know, the limitation of it. All right. Cool. Think. Have I filled your brains up yet?
Yes.
Okay. So we did that. Cool. Bond over to 3. Oh yeah, I forgot to do that. It's supposed to be diamagnetic. All right. Because all the electrons are paired. I don't have anybody empty.
So
Everybody's got a buddy.
if one of them's empty, then it's the pair of
What's that?
So if one of them's empty, that's the pair.
Paramagnetic, yeah. And we'll start with that next time. So,
My brain.
yeah.